So this is a continuation. So by the way, this is discussion 113, December 14th, 2023 for parallel quantum algorithms with PyTorch and Keras and QiML. So this is a continuation from last week. And so basically, I came across this model and I iterated on it twice, but I never really knew that you could take this up to an nth degree and it wouldn't cost exponential amounts of RAM, or at least significant RAM and so significant runtime. So kind of where I left off last time is this 8 of these 4-qubit embedding layers. And it's been, giving good performance. And I'll show you some other algorithms too. This model is by Thomas Bromley at PennyLane, or Xanadu technically. And there's 2 versions. So there's a PyTorch and there's a Keras. So Keras is a part of TensorFlow. So the study I'll show you here is it shows several advantages of running quantum circuits in parallel versus a single circuit. And, in specific, a substantial reduction of runtime and resource requirements per qubit. So if I take a 16-qubit circuit versus a 4-qubit circuits, I'm getting similar types of accuracies, but I'm getting significantly less RAM and significantly less runtime. So you could see that with the 79 seconds for 16 qubits and 32, and it gets worse and worse to the point where you can't even run these circuits, especially in the 50s, and if you're doing quantum machine learning, the 40s too. So, with a 4x4 circuit in parallel at 20 seconds and 2.1 gigs RAM. So basically, I pulled all this together, and I want to test on at least 2 platforms always. So you see, I did Qiskit and PennyLane last week. This week, it's all PennyLane, but it's 2 different PennyLane models. So in specific, I was able to get a model with 80 quantum algorithms in parallel to get 100% accuracy with modest RAM and runtime. I haven't done the calculation quite yet, but it's definitely not exponential, and it's something that's feasible to run, say, hundreds or thousands or even more than that of quantum circuits in parallel. So any modification to the algorithm type had low impact on the parallel circuit model. And then what this means is basically it's robust to changes. So we call this, robustness. So small changes does not affect the performance of the model. And I guess the main drawback is it's using low batch sizes, which is typically associated, to get its best peak performance, like lowest loss, which is typically associated with a little bit slower runtimes, but this is not the big problem when compared to high qubit circuits, right? So, we can deal with these lower batch sizes of 2 or 4 as compared to 20s or 30s or even 40s of qubit circuits. And the learning rates in general did not have a big effect on the parallelized algorithm. So they just didn't seem to change no matter what, if it was lower, a little bit higher, in between, say, a little bit below 0.2 and then up to 0.5. And I'll show you these as well. And data set complexity only slightly decreased, and you would expect to see this. You test all these things ad nauseum just to try to break it, right? So increasing complexity from a noise of 0.1 to 0.11 all the way up to 0.2, it decreased the performance slightly, but not as much as the circuit model. Now, the big thing with the Keras model is the single circuits on those didn't seem to match up with the PyTorch single quantum circuit. So those performances seem to be lower than what would be expected. Okay, you would expect to see similar accuracies and losses for a single circuit compared to 4 times, or whatever times that, to get the same number of qubits. And then these 4-qubit parallel circuits showed very little overfitting at all. One of them actually, it's the training loss and the validation loss was actually identical, for the final epoch. So you can study these over the course of epochs, and I took the last epoch, or the last run of all these, and compared them, one by one. Okay, and then, so this one I'm going to work on a little bit more, but basically what it's showing is this is a continuation of last week so this would be called a 4x8, this top one. So it's a 4-qubit circuit, and there's 8 of them. And on a technical thing, which is more last week, and this is more results, on the technical thing, you would need 32 of these classical neurons going into these, as opposed to running a single 32 qubit circuit. So this is the thing. The number one thing, no exponential RAM, no exponential runtime in these models. And here's another 4 qubits. So this would be a 4x2. So you see 8 total qubits requiring 8 classical neurons. And then if it's a binary classification, the end is always 2. Okay, so this one, these are some algorithm studies. So basically, we'll go left to right. So this 4Q1L, it's a 4 qubit circuit with 1 layer, meaning it's a regular circuit. And it's represented by this burgundy. So you can see the loss was a little bit higher than the other model. And it almost reflects, and it's not always the case that a low loss is high accuracy, but it oftentimes is like that. And you see it pretty well traces itself with its corresponding accuracy, which is in red, or this light red here. And then the next one is a 4x8, meaning it's a 4 qubit circuit with 8 layers, or 8 circuits. And then you see that the loss is lower here. And it corresponds to a higher accuracy. When it gets really low here, the accuracy gets high here. So, in this specific case, it's basically, it's based on the algorithms. So this is an unconventional look for a graph because all of these algorithms are different. So say, for instance, IQP embedding is very, very famous and people want to use this in the future. And then here's 2 repetitions, by the way, of IQP, and then doing IQP with another embedding. And then also, instead of the main algorithm, is this RX embedding with basic entangling layers. So that's what BEL means. And then these last ones are basically showing, with the parallel algorithm, keep adding onto gates, and you get this decreasing loss like every single time. Like, you typically don't see this. You see some jumping, to get your accuracies. But as the number of embedding gates went up, the performance eventually went up to 100%. Okay, so for this last 7, so these are 7 rotational Y gates that are embedding. They're not trainable like some of them on the previous slide. They're embedding, so the angles, it's not like machine learning. It's just to convert classical to quantum states. Okay, so this next one is basically, you'll see this one in other literature too, probably. So it's basic entangling layers, which is a trainable portion of a variational quantum circuit. And say, for instance, if you have 1 layer, 2 layer, 3 layer, there's typically changes that occur. So I want to stress again that the PyTorch model was consistently reliable as far as like, okay, this is expected to happen and this is expected to happen. But what was unusual about this with the parallel algorithms? So this is basically it's a 4x8, so 32 total classical neurons. Is basically, it didn't really change, right? It didn't change over the course of, so 1 run is 1 layer of this, trainable part of the circuit. And then another run is 2 all the way up to 10. So it just didn't change at all, really. And you see that reflected with the green at the top. So, it could mean a number of things, needs a harder data set. It could be just saturated on, performance. It's pretty close to 0. So for this particular one, it might help to bump up on either a noisier data set or a more challenging data set. But it also goes to show that in this particular one, it didn't experience all of this shiftiness of this red, which is the accuracy of a single layer of, 4 qubit circuit. And then you see the corresponding loss with it. So these 2 go together. And with a single circuit, it's showing all the shiftiness, but with something that's taking that single circuit, having to add 7 more to equal 8 in parallel, is that everything's just, more flatline. So again, this particular one, could probably use a harder data set to see if there was any potential gains in changing the layers. But this study is quantum machine learning. There's quantum circuits with quantum algorithms, and the individual parameters, just like in machine learning, they get optimized, just like in classical. So it's rotations of quantum bits. Now, this particular one has a lot of different runs here. Now, I'm going to start from left to right. So this is basically validation loss and accuracy is on the left, and on the bottom is the model type. So the first one is a standard 4 qubit algorithm, 8 qubit algorithm, 12, 16, and so on and so forth. And then it gets up to this, so 4x2 would be 8 equivalents, 8 equivalent qubits. So you see that the loss was a little bit higher there. A 4x3 is that 12, which they're pretty similar, as far as losses. You want lower here. 4x4 would be something like 16, and this is where it actually goes lower than the 16. Now, this is a huge deal. So if you look at the right, so it's for the per qubit used, okay? So if you want to use a 16 qubit circuit, in this case, it was costing 32 gigs of RAM. That exceeds by double a V100 on NVIDIA, or it's an NVIDIA on Colab, and that's getting up to an A100, which is 40 gigs. But I was running high RAM CPU, which is 51 gigs. So anyways, that was costing 32 gigs of RAM on that particular one. 79 seconds, and then the 4x4 only 2, which is basically flatlined. It really didn't pick up. A lot of times you might start running it at 2 gigs, and it's only running for 20 seconds. Now, and this is all for classification, and this is data set mapping through quantum mechanics to get these accuracies. A very similar accuracy for the 16 all the way up. And if you take these up, they're about, similar, 99.5. Sometimes, actually, these would probably be the 99.5s. So going on with this is basically, I continued it. So it's a 4-qubit algorithm, 5 times in parallel, 8, 10, 20, 40, 80. And the 80 is the one that seemed to be the lowest loss. I took it up to 100 too. And these are not significant figures. Like all of these experiments were run either on a high RAM CPU, which gets you, a little like double the speed of their standard CPU on Colab. A GPU wasn't used at all in these experiments. So, basically I took that further. So based on the Keras experiments I'm showing you with the best learning rate, with the best batch size, this 40, so it's 4 qubits with 80 algorithms in parallel. And then I'm calling it P2, or my performance 2, was able to get this loss of 0.0007 when compared to the accuracy of 100% on that specific one. So I think the thing that stuck out is that it was always, predictable, as far as, a lot of times just keep adding embedding gates, or in this case, fix the other aspects of the model that would help it even more to get this 100%. And then, are there any questions? So that was the PyTorch, and the PyTorch model ran faster. I had to fix this Keras model anywhere from the just the original version of Keras to get this to run. But it's still, a lot of these upcoming studies are very interesting. Any questions at this point?
I have a question. In the earlier slide, is it like when the loss is getting 0 and the performance is high, like there is a case for overfitting, right? Like, how are these addressed in this model?
No, I'll show you. I did some overfitting studies too. So if your training loss is going to 0, and then your validation loss keeps rising, so that's typically, you'll see the training accuracy go high and the training loss being so low. But these are validation. So these are validation on, like it's not. Yeah, and I'll show you in the upcoming one, because you want training loss and validation loss to kind of train commonly. And I've had other experiments where it's basically the loss, you'll see training goes to 0, and all of a sudden your training accuracy goes to like close to 100%. But these are actually validation. And so yeah, that's typically the case, is you actually see both of them. And if memory serves me right, and I'll put the tables up too, is that typically it would actually, your training loss and your validation loss would be very similar in values.
Got it. Thank you.
Anybody else? So, and again, with these Keras models, and I still haven't figured this out, because there's, even Penny Lane says try to run PyTorch, but you can't go into an industry just running one, right? Like, figure out what's wrong with one of them, which is the Keras in this specific one, and you have to troubleshoot it. So basically, all these ones on the top are single circuits, so they're probably high, when compared to the PyTorch ones, but it's still interesting to see because I still can get diagnostic batch sizes based on the types of architectures I wanted. So the first two that show up here is they're 6 qubits times 8, so it's 32 effective neurons, and its lowest overall loss was at this batch size of 2. And then it was the 8x8, this 8Q8L, the purple one. These both a batch size about 2. And that's what I found is going over to Torch with these is, plus or minus. And if you get up to like hundreds or thousands of circuits, you might have to, adjust it 1 or 2, something like that. That's how it's looking like in this current, model/system. And the one that was used the most is this 4 qubit, 8 layers. So this is 32 effective neurons and, with a batch size of 4 right there. So, some might say that if you didn't have it tuned correctly, or say somebody's done this study before me, right? And they just missed completely on batch size because they just wanted to go fast. Well, a lower batch size is not nearly as slow as going up more and more with qubits. And that's just how these are. So the author's models on both of them, he chose to use, this is Thomas Bromley, is 5. So actually on some, say for instance, like with higher layers or higher circuits in parallel, I did find 5 was, better than 4, but typically it's somewhere around here and your peak performance, might be with this, 6x8, 32 effective neurons on that specific one, that black one. Okay, so this next particular one is based on learning rate. So if you ask and you try to find out what are you supposed to tune first, these are machine learning, like very typical questions, learning rate or batch size, and you can tune them separately, and that's what I did. But then, you start having to merge together, and there's significant amount of time you could do just to squeeze the juice out of, whatever you're trying to do. So in this specific one, you see that if you were to focus on anything on this one, it'd be the top and bottom line. So that's with the parallel circuits. Okay, so you actually, at some of these points, actually getting that 100%, say anywhere between 0.18 to 0.34. And again, this fixed to 4 qubit, 8 layer algorithms. Now, the ones in between, like I said, with the Keras, with these single circuits, not quite running it as good as the ones on Torch, but the takeaway message on this slide is basically this, is that no matter what the learning rate was for the parallel algorithm, the loss and the accuracy was not affected much. So I guess the term that keeps on coming up if you do analytical work is robustness, right? So does small changes to a model, like if you change from 0.2 to 0.22, is that going to break your trends in getting good performance at this level? So this is good to see. And again, the information that I took from this is basically, if I use this, say like a 0.27 for something, that I could use it on Torch, and it didn't seem, it seemed like it was effective doing these studies on Keras too. Now, this next one's interesting because, it's a smaller data set, but there's things you could do with noise to make it significantly more challenging. And, again, the first thing that focuses on the parallel layers, because these bottom ones, it's harder to compare against because Torch did much better, is when you increase in noise, so you get up to 0.2, how much does it break the model, right? Like how much does it break the, your current architecture? Technically, it's a torch.nn or Keras, these neural networks. And you see it doesn't affect it much. So, and in fact, you see this steady incline, which is likely a good sign, so increasing the data set noise, all the way up to this 0.2 is not, affecting the accuracy and the loss as much as it could. Right. And it's just good to see from all these different angles, learning rate, batch size, and, learning rate, is that that's what you have to do. If you hold off from trying to, figure if this whole thing works, then, you'll find out later. So why not try to find out what's really working here? So yeah, so this specific slide is just, steady increase in loss as the accuracy decreases, as the data set gets more and more challenging up to this noise of 0.2, which is that last value there. And then on this specific one is, this is the overfitting slide. So basically, by the time it got to this 466L, and actually, I think the reason why I stuck to this 4-qubit 8 parallel circuits is because the training loss and the validation loss were actually the same. They're the same exact values. Now, I don't think they trained the same, like say every single epoch going to it, but they were close. So that's what showed with this. So the orange line here is the validation loss, and then the green line here is the training loss. And then you could see, as in this specific case with the single circuits not doing well on Keras, all of these having a huge gap, meaning that there's a higher chance for, overfitting, especially, because the training loss is low and then the validation loss is high. So that's not wanted. And then as you go, 4x2 up to 4x4, 4 qubits by 6 layers, you see that the distances between the two losses are good. And these are good to see. And you can see, especially with these last 4 models tested, that the accuracies are pretty similar. As this goes up, the accuracy goes down. So again, checking it, looking at things from all these different angles. Now, I will say this, it was a little harder to get all of the, you get training loss, training accuracy, you get validation loss, validation accuracy with Keras. And I couldn't find an effective way to do that with PyTorch. And that was one of the reasons why I did that with Keras, is because it was just working. And it's not like a broken thing. It's just like, you have to find a way. So basically, what the study shows is there's several advantages, right? Because, this, and I'll have all the notebooks and all this stuff on the repository. And, it just seems like it's a far more effective way, because if you want to reach a specific loss, and you have a good algorithm's number one. If the algorithm's not good, then no matter how many circuits you put in parallel, it's not really likely going to get to this extremely low losses or, good accuracies that don't overfit, those types of things. So you'll see a lot in this study with the embeddings. So I tried the IQPs. I used the 4 rotational Y gates as an embedding. And then in the very first slide, with the PyTorch, I actually used the, some of these other trainable basic entangler layers. And it didn't seem to help too much with the parallel quantum algorithms. But again, I think that could have been a thing. I could have made the data set more challenging on that specific one. And I haven't found a limit. Like, I really haven't. If you run, 80 qubits, at a lower batch, and you're only using 5 gigs of RAM, and they're in parallel, you can't get close to anything. If those are 4 qubits, that's 320 effective neurons. Like, you can't get anywhere close to that in simulated qubits, state vector, maybe tensor network, but that gets into approximations. So these are state vector exact algorithms, right? So, that's the way it's looking. It didn't seem to have a cap, and I didn't go up to, it's more of a coding issue, right? Because if I type in, if I want 20 more, I have to change, I have to add, say, let's see, 20 more layers. Let's see. Well, it's multiplied. I don't have to do 20, but if it's 4, I have to do 5 more, because it's 4 5 times 5. So I have to do 5 more up in my neural net. And then for my forward method, I have to do, several lines down there. So it's more of a coding issue, and it probably can get automated. If you want to go up to thousands of qubits, and then, you think you have a good quantum algorithm, it's just, not, say, like, reaching that low loss, or you're getting the fluctuations, as you increase or decrease learning rate and batch size, it's just not behaving predictably. That's what it's looking like here. Is this will fix it, just run in parallel. And so, and I'll plot this, and actually might be sublinear, as far as like, it's the more algorithms you run per qubit, it gets faster. Okay. because there's some overhead in the rest of the notebook. But in general, you're, not paying for it. And, with time. And let's see. And again, I think you see with a lot of these is it's just that. It's like, you look for robustness. Like it's something like some minor change, like they call it real world evidence or real world data. You get out into the field and you run your model, and then just something's just a little bit different. You had to tweak, and then all of a sudden just nothing works. I think with this, and there were several experiments that showed that it just didn't, behave like that. It was robust to small changes and not changing in performance. Okay, and then there's also developer framework. The past two, I think this it was last week, so that'll be up on the repository as well. Now, are there any questions? I saw a number of new people kind of come in here. Any questions regarding any of the Torch or Keras slides?
It's great information. How about that?
Yeah, thank you. Yeah, and it just has to get further iterated. So the reason why I can get a lot of comparisons between a 4-qubit 1-layer and a 4-qubit 8-layer in parallel is because the model itself was coded to do that. It's a better comparison to say but the qubits are different. That's what makes it trickier to say if I want an 8 well, that would be too hard to do, like, for most systems. But if I want like a 16-qubit, a single circuit, and then 4-qubit times 4 at the bottom, the model how it is right now are feeding off the same number of qubits. So you just have, would have to code. But anyways, that's a more productive experiment, is by qubit as opposed to a single circuit compared to a parallel circuit with just more and more layers. So that's a potential improvement right there. Anybody else that we haven't heard from? And I guess this talk, and this will be up as this is being recorded, this talk is aimed towards those that have struggled with, RAM, running out of RAM, and that's easy to do. Like even the new H200s with 141 gigs of RAM, that's nothing compared to like, if you want to run like 40, 50, qubit circuits in a full machine learning environment, that's going to be hard to do. But if you could do it in parallel and take advantage of quantum effects off of each of the smaller algorithms and get the same, sometimes even better performance while saving all that RAM and time, that's probably a better approach. And I'd be interested kind of, I know some people's backgrounds here, kind of where you're coming from. I think that, we're at that stage where things, kind of like, split as far as the different groups going to different areas. But there was actually a picture, I think Terra Quantum had up, and it says quantum inspires something. And basically, pointing at they'll be using, CPUs or GPUs for a lot of their experiments, as they also, posted in a different headline. So, but yeah, does anybody have a specific question regarding the two libraries? The PyTorch, which I covered first, or the Keras?
This might be Noah's question. How big is the data set? Like,
yeah, so this is small. Yeah, so it's 200, and one of the slides I went over, I increased the noise to like where it's intermingling and there's not too separated. But yeah, this is the next steps. It's hard to screen, as you get bigger and bigger data set as far as data points. But as far as complexity, you can always make it, more complex.
Oh, okay. And are these like PyTorch or Keras like our open source code to understand like how the layers were distributed between PyTorch and Keras?
Yeah, so Thomas over at Xanadu, he did a pretty good job, or he did, he figured it out. And, so basically torch.nn, torch.sequential, and there's Keras equivalents. And I'll probably wind up having to do a demo at some point, because say for the Keras neural network, the framework is a little bit different than the Torch. I actually think it's a little bit easier for the Keras. And there's all types of stuff. I think the main thing is to focus on the parallel, and because the quantum circuits themselves, they can turn into neural networks, right? As opposed to figure out the small stuff, like fix the algorithms, which we have plenty, and just this is a new application, on a bigger scale that's tested every which way.
Okay, thank you.
Anybody else? And I think just if you want to do neural network kind of stuff, it's not that hard. It's just you have to find the patterns, and it can be frustrating. And there's a number of resources on the web to ask. So you can ask, like, what does this digit mean? And it'll say, like, this specific digit is the number of elements. So say, for instance, like, in Keras, it might, that number 8 would represent to x1, x2, all the way up to 8. And then it means something different in Torch. So there's a number of resources out there that can, help you step by step to understand how to modify, different architectures. And if you missed it, so I found these because I did all of the Qiskit and Penguin machine learning demos twice. So that was done to basically to find things out. And I wasn't expecting to find out the good relationship between increasing number of parallel layers that I found last year or last week. So, you'll just find things, and you'll have to go through a lot of code. And eventually, you just find something, and then if that doesn't work, just keep on it, right? Because that's what kind of makes or breaks the innovation or new opportunities. Anybody else that we haven't heard from? And I guess some other things that have come up is basically, always start with the algorithm. If the algorithm is not something that's performing well, say it in a different demo or your own demo, it's not going to work well increasing the number of layers. It's just, that's not going to happen. So I just, switch some things around, but I included the algorithm first. And, basically you have to, it's part experimental, it's part reading and literature, these types of things. And then, are there any questions regarding quantum machine learning, or effectively it'll all be quantum inspired machine learning from here on out for a while? And I think, this is going to attract a crowd, right, from deep learning, and they're used to deep learning parameters, and these are different. And, even though, you can get great, awesome results with parallel circuits, these types of things, it's still, I don't think it's 100% based on, say, papers within the past 3 to 6 months, as far as, this specific, algorithm for this specific data set types, and, not having to change the algorithm. But with this one, doing them not in series, it seems to be more forgiving, as if the learning rate's off, if the batch size, like, people might have tried that, but that's the other thing, is if your batch size is just way off, you're not gonna, and you don't find out what the optimal batch size is, then it's not gonna work in a bunch of experiments, or it's not gonna give you the best performance, because it's forgiving, but it's just not optimal. And would anybody like to share anything as far as, coming from machine learning? Anything you could share from, quantum algorithm perspectives too, the different experiments that you run, and what works best for, certain types of experiments as well. And I guess, as a, fully complete this, these sets of experiments is in the future, it'll all come down to, proving that this in specific aspect of quantum mechanics, whether it's like, what it does for embeddings or super entanglement or, these type or everything, quantum related, what is the difference, performance wise between the best available classical algorithm, existing, and then what does this new thing offer? So this whole study I've done basically says this is to get better performance over a single circuit. And, it's a big step to take. And then the next one would be, okay, now the algorithm itself, what is so uniquely special about, turning these rotational, qubits in this specific manner in a more predictable way? Because we can have good embeddings, and I've had good embeddings, and I've had, by the way, several studies where increasing number of layers of trainable, quantum parameters, and, more layers helped with better accuracy, that type of stuff. So, that's the breakthrough, right? And obviously, with all these organizations, you can't deny, like, and they've had, now they're focused on quantum inspired, the Sandbox AQs, Terra Quantum, people in industry, National Labs, Brookhaven, NERSC, Google Bard, using QiML, or, so yeah, it's these types of things, right? So it's not just fun to do quantum, it's just, this is a particular way of using quantum mechanics that, that we're 100% confident in. Okay, so there was something in the chat here, the enabling of the scaling aspect. Okay, so this is Dwight. I may have a specific on and okay. Yeah, so you always want scalable, right? And if you were to say something, if you do, quantum algorithms that you're capped off at 30, even using GPUs, and you need higher dimensions, like your data just has higher dimensions, and your only other option is tensor networks, then yes, it makes sense to take in higher dimensions and then just split the load across multiple different, circuits. So yeah, I think it's something that, it's worth also getting good results on, because I'll have all these up, and, the more the field, buys into this, because those are the two main options. State vector circuits, they're exact, but they're exponential in RAM and exponential in time with more qubits. So, going wider, a wider circuit. Tensor networks, they're approximate. They can go higher dimensions. However, they're, the main thing is basically the approximate aspect. Now with the parallel circuits, it seems like you can go higher dimensions, split the load across the same, multiple algorithms in parallel, and then, you're keeping that preciseness. So like I said, this is classification. So this, this looks like it'll work for this. Dataset separation. But yeah, there's a number of things you keep experimenting and keep trying to figure it out. But based on this week and last week, it looks like it's a robust model, especially this week, that changing the learning rate doesn't change it that much. There is an optimal batch size, and you can deviate a little bit from optimal performance, but it's, even if you ran high, it's not going to break it. So. And then anybody else kind of specific experiments with the QiML stuff, quantum machine learning? And for those that haven't seen, the previous, say 3-4 weeks before that was setting all this stuff up. Of like November 13th of last month was, you had NVIDIA across these three, NVIDIA GPUs, but AMD you can also use in some of Penny Lane stuff. But it was BASF, Classic, in an Israel hospital, and then also Terra Quantum saying immediate financial impact using, this is basically quantum algorithms with GPUs. So I think the extra credence with this study is that it was all done on high RAM CPUs. So higher RAM than an A100 GPU, but I didn't get anywhere close to that on any of these parallelized ones, just basically 5 gigs of RAM. So and then anybody have any specific, machine learning questions? Now, unless you become familiar with it, because people come from all over, so say for instance, like a simple question, you could just ask a question about batch size. What's the importance of optimizing batch size and what is batch size? And likewise, if you ask about learning rates and what does that actually mean? Because all these things in the back of, developers' head, they just know these things. So any specific questions on those two? Just basic machine learning questions does anybody have? And, so this has all been building up, but basically batch size. So say if, in this specific case, 150 training samples go to training, and then 50 go to the validation set. Okay. So that means that of those 200 samples, 75% went to training. Okay. Now, when you talk about batch size, it's referring only to the training set. Okay. So that means that if you have a batch size of 1, it literally does 175 separate iterations for an epoch, okay, which is slow. And then if you have a batch size of 175, it means that all of them go through all at the same time, which might not give the model enough time to learn, say the parameters, these types of things. So you deal with this whole area between basically 1 and, the max number that you have in there, that 150. And then you can kind of, try to make sense of what's the most optimal batch size, in that specific thing. And there's a demo up on deeplearning.ai that actually lets you adjust these things. And they actually have the most direct route being the one where, your batch size is equal to the full 150. In experimentation, you try to make these things make sense in your head. So, if you're splitting the load between multiple algorithms, you think the batch size should be higher, but in fact, it's lower. And, it's these types of things, right? But, some things are experimentally determined, and you have to have a good idea of where you need to be, like around this batch size, around this learning rate. And then as you shift parameters or hyperparameters in other directions, you have to know how to kind of like adjust with that. So, they say, even QiML, at least $5 billion by the end of this decade, and compounding annual growth rate, something like 30-40%, I think closer to 30%. In machine learning on its own, you could see it for medical, you could see it for all these different areas, that it's a field that is likely going to have a significant impact on multiple industries, because we're trusting computers more and more and more, right? Anybody we haven't heard from, Ron or Samuel? If not, Gil or Edwidge?
I'm just enjoying the talk, Kevin.
Yeah, and I guess to back this up, I do an AI ML, I'm not the host on Sunday mornings, but it's a really good talk that a colleague of mine gives. He's in Boston. You can find it on the meetup. It's like machine learning and Kaggle. And basically, we talk about the things surrounding the industry, which are GPUs, so no matter what you use to develop applications, eventually in industry, especially for training, if you're not running inference on a patient single data set, they're likely going to be on GPUs. Now, for the longest time, it has not been ruled by data centers or auto. It was actually gaming. And actually now in the projections into next year, I think it's 3 or 4 times bigger they project for data centers kind of taking over all these other industries. Okay. So this is, totally like, I believe the A100s and these GPUs and the collabs that I use, that's considered data center. And you'll see that kind of, it was that barrier, right? In 2017 for, well, at least in FDA, for them to use deep learning, they broke through a company called Keras. It's cardiovascular software's medical device. Saying they broke through, and then just right after that, like now there's like 500-600 a year, that are approved with those types of convolutional neural networks. I'm not sure about transformers, but probably, and then if not, pretty soon. So yeah, now that everybody trusts it, it's just the next hurdles, right? So this is this is classical data processing and classical data generating, all of this that I discussed. It's simulating quantum algorithms. So yeah, so the specific meetup, yeah. So this, like I said, it's machine learning and Kaggle. I think that's the exact name, and that's Sunday mornings. And there's so much in the history of AI, and it's been through winters where the hardware wasn't there. And then all of a sudden, late 90s, early 2000s. And now we're talking trainable quantum parameters, with QiML. So yeah, that's that specific one. And you can, feel free to ask questions of that. And there's actually all of this that I'm talking about as far as the frameworks with Penny Lane and, quantum algorithms being used with medical data. It dates back to 2021. And this is for COVID, right? So after COVID, like rheumatoid arthritis, and I did a bunch of brain tumor experiments, which I could probably rerun now, at smaller qubits, to make it go a lot faster. It's just a matter like the code meshing. But yeah, there's been, IBM, Amgen did one as well. And I just kept seeing the same type of results, like single 4-qubit algorithm, Hadamard gate, embedding, some rotational embedding, and then a bunch of CNOT gates, which are 2-qubit gates. And, the results are just kind of similar, right? But it's just, I think when this all will break through is understanding like, this is the true limitation of state vector algorithms is the RAM and the runtime. So again, so if you can run them in parallel and get all of that quantum information, when your data set, is processed, like the results here show, then, that makes a lot more sense, right? So quantum mechanics good, but, using a lot of GPU resources and time is not. So yeah, and there was a comment there from Samuel there. He says he thinks of quantum machine learning for analysis of cancer, HIV and others disease. I'd say that the vast majority has been images that's been done that I've seen. And, like say, for instance, the Amgen IBM is, I think that's EHR data for rheumatoid arthritis. There's another one, osteoarthritis, those types of things. But yeah, I mean, you have to do, this is fundamental research, like just running a ton of experiments and, figuring how or what's wrong with it. And I'd say for the most part, except for, the lower batch sizes needed for optimal performance, everything else is kind of like working very much in the favor of parallel algorithms. And again, low batch size that you have to use because that's the best performance is a lot faster than if your quantum algorithm is either really, really, really slow because of too many qubits, or it just won't run because you have way too many qubits, right? It's just there's not enough resources in the world to do it. So anybody else that we haven't heard from? And then I saw Pacome or Dwight. And then if not, yeah, go ahead.
I was just saying, Dwight here, I put up that chat about access to the earliest actionable intelligence, which can drive those algorithms that we want to be able to measure. on performance, and I've got some systems that we could probably apply this to. So let's take a look at that at some point in the future.
Yeah, I mean, you mentioned the word, so scaling. Yeah, everybody wants scalable technology, so this is software, right? I use hardware, CPUs, GPUs, but it's all comes down to what's available primarily with Penny Lane. And I can do some things with Qiskit too, but yeah, it's looking good, right? So bigger data sets would be the next thing. And again, better comparisons, like a 4-qubit single algorithm, because that's what available in the model, versus 4 qubits and so many layers is best if it was like 32 qubits versus an 8x4, right? So just have to continue to try to, it's basically making sure it 100% works. And then anybody else that we haven't heard from? So this week was all just running experiments, and then it was all building up to this. Okay, we're for sure sticking with this technology. Several other huge companies are sticking with this. Quantum algorithms, GPUs. Are there any other questions? Hardware, software related to running quantum algorithms. Anybody we haven't heard from, Ricardo or Carrie?
I'm just listening tonight. I've been stepped out of quantum for about 3 months, so I'm coming back in. So give me a minute to ramp.
Yeah, and it's always interesting to see where people are coming from too, because I remember joining your discussion there, and it's kind of like the most practical technology that scales. That's the one that'll make it.
Absolutely.
And it's all important. So I know some of you at least are very strong in quantum algorithms, right? So this is important, but the next step is, how does it relate to actual, real data sets, test all of your algorithms on, so that half moon's data set, you can change the noise from 0.1 up to whatever. And all of these points are basically intermingled, and, it's just harder to do. So, there's just a number of things that you can really do. Don't just focus on a single algorithm that could be, you want to actually test it on a variety of data sets. And, this is a good one too. These types of things, I guess the practical nature of it is what I'm mostly considered with. And then anybody else, and feel free, you could put it in the chat as well. So we had some things as far as, yes, scaling the technology, and then, for medical work too. And, others, there was a blurb about, we haven't talked too much about IBM. This is supposed to have been Xanadu or Penny Lane. And they have somebody else that's doing QML or, this, work with GPUs and quantum algorithms too. And it wasn't quite clear to me the association, but I had asked at one point, are you getting more tutorials? So Penny Lane has like 26 and Qiskit has 12. And, there's just more you could do with the Penny Lane. And they said they will at some point. But I don't think the whole world is bought into it yet, as far as, GPUs, quantum algorithms, where there's a small number of us, but the news is definitely prevalent. And then you see some results here today that are saying, okay, we can actually do a lot here, and we don't need other things. So and then anything else that we haven't covered today? It could be anything. If you're just struggling to get up and running, just any of the Penny Lane machine learning models are pretty good. Some are a little bit more complex than you or I. You have to spend significant time to research and understand them. But the proof is in running, right? It's not just researching about it or thinking that you have the best one. It's actually, okay, did this actually run with this specific data set? And then solving hundreds or if not thousands of issues that come up along the way. So that's just, that's how it is. And I'm trying to think, anything else? Any other questions or comments? And again, feel free to put in the chat there. Trying to think, as far as events go, people are different learners. I like to learn off YouTube and just, trying and just figuring things out on my own. And there's a number of people I know in this group, at least, that have gotten certificates, which are really good. And you could speak on those too, if they've been QML or, quantum algorithms, those types of things, and how basically what they've done for you. So, feel free that, you can chime in about that too. And yeah, like I mentioned before, on the AI side is there's a lot of Python, but it tends to be just more general, especially on Meetup. LinkedIn, I don't know, it doesn't seem to be, I can't find what I need right away. But there's, if you type in machine learning, Kaggle, PyTorch, TensorFlow, Keras, these types of things, you could find those things. And the work that's shown here is a lot more deep learning and less, quantum algorithms, even though it's a really important part, and that's what distinguish it, with performance, but the bulk of it is still like, cranking through the batch size, learning rates and, data set challenges, those types of things. Awesome. And then any other last comments or questions? We're coming up on what many people do in the US is the holiday season, and it's kind of been like that for Thanksgiving. So just, make sure if you are coding and developing, take a break and, enjoy the, all the festivities around. So if you solely want to speak on that, as far as wishing everybody a happy holiday, you can do that as well. Awesome. I appreciate everybody coming on. And so this will put us, let's see here. Yeah, so this has been 113 discussion, Thursday, December 14th, 2023. And this has definitely been for the parallel algorithms, with PyTorch, Keras, and PennyLane. So thanks everybody for coming on. Have a good rest of your day and have a good rest of the week. Take care, everybody. Happy holidays.
Thank
Thank you,
you.
Kevin. Take care.